So, now we will see at one technique of midpoint voltage balancing. Okay. Now, one thing that I will have to say here is why are we so much concerned, why there has been so much research on this midpoint voltage fluctuation. If we can get a very good PWM strategy or a switching strategy by which we can make the midpoint voltage fluctuations very small, then automatically it means that the capacitor size will go on reducing, right. So, because you can see here that we are, when the midpoint is accessed, then a certain charge is being either taken out or inserted into the midpoint, because the I0 current is flowing. If you apply for a certain duration of time the 0 vector, the 0 this whenever the I0 is applied, then that amount of charge is either taken from the midpoint or inserted into the midpoint. So, there it will cause a fluctuation. So, the certain charge is taken. So, therefore, if you increase the size of the capacitor, the fluctuation in the voltage can be minimized. So, but on the other hand, if you can make sure by PWM that net charge over one switching cycle is made 0 in a very small duration of time, then the size of the capacitors on the DC bus can go smaller and smaller, which is very much advantageous, okay, because capacitors are bulky in size. So, therefore, a clever technique of balancing the midpoint voltage not only improves the harmonics and not only makes that no devices are subjected to a voltage of Vd by more than Vd by 2, but it also ensures that the size of capacitors are small. Remember that in MMC, which we had studied earlier, in MMC the size of the capacitor is much more than that of an NPC, maybe 3, 4 or maybe 6, 7 times. Okay. The reason why NPC has lesser capacitance is because we have multiplicities in the switching states. Okay. This ensures that the net charge which is flowing in or out of the capacitor, first of all the NPC has a single DC link for the 3 phases. Okay. That is one reason which the MMC does not have. Okay. The MMC cells have capacitors which are like a single phase supplying. So, the MMC has a current which can help in getting the capacitors back its charge only after half a cycle has crossed, but this is not the case with NPC. In NPC we have different switching multiplicities which can ensure that the voltage which can ensure that the charge taken out of the midpoint is quickly restored or the fluctuations can be minimized. So, this is the difference between MMC and NPC, where NPC has a much smaller capacitor as compared to MMC. MMC does not have this option. MMC has to kind of like design the capacitors in such a way, it is a big capacitor, because you take the charge from the capacitor in one half cycle and you can give it back only in the next half cycle. So, it has to hold the voltage for half a fundamental cycle. In fact, for that reason, if the fundamental cycle is very big, if the time period is very big, for example, in motor drive application going to lower speed 0 means 5 hertz, 0 hertz, close to that speed, then this half cycle is very big in time. So, the capacitors have to hold the voltage, which is not the case with an NPC, because we have multiplicities, and also NPC has a single DC link for the 3 phases which the MMC does not have. Okay. So, let us now come back to what we were discussing, and we will now see how we can make the midpoint voltage fluctuation minimum using some clever PWM techniques. Okay. So consider this reference vector OA. Okay. So, for this reference vector OA, the switching so these are the 3 enclosing vectors. So, their timings which I have written here in this table. So, plus 0 0, plus 0 minus and plus minus minus and 0 0 minus, these 4 will be used, right, and their timing duration for example is like this T 0 by 2, T 1, T 2 and T 0 by 2. Okay. Now, suppose the total sampling time or the total switching cycle T s is which is equal to T 0 by 2 plus T 1 plus T 2 plus T 0 by 2, that is sufficiently small. Okay. So, we have quite a high switching frequency. So, that the T s period is so small that the magnitudes of these currents do not change in that switching cycle. Okay. Now, net charge in the one switching cycle T s is I b into T 1. Why? Because when we apply this plus 0 0, the timing duration is T 0 by 2 and we have just seen that the current which is flowing out of the midpoint is minus I a. So, the net charge which is going out of the midpoint is minus I a into T 0 by 2. Similarly, for T 1 duration we access the medium vector plus 0 minus and the midpoint current is I b. So, I b into T 1 is the net charge which is taken out of the midpoint. When we access the large vector, the midpoint is not accessed. So, we do not, so this is 0, and then when we have the complementary state 0 minus minus, we have I a into T 0 by 2 as the net charge which is flowing out of the midpoint. Okay. So, if you add all this in one switching cycle T s, this and this will cancel, this term and this term will cancel. So, that the net charge which is flowing out of the midpoint will be equal to I b times T 1, right. This is what is going to cause the fluctuation in the midpoint voltage. Now, we would like to make this equal to 0. Okay. We do not want the midpoint voltage. So, we want the midpoint voltage to be the fluctuation to be equal to 0 in one switching cycle T s. Okay. So, we want to do that. So, how can we do that? Note that the one which the technique that we will use is this T 0 by 2, right. So, we have two vectors of equal magnitude, this plus 0 0 and 0 minus minus, they are producing the same vector, okay, and their timing durations are T 0 by 2 and T 0 by 2. If we change these timing durations to a value which is not equal to T 0 by 2, for example, this is 0.5 T 0, suppose we make this as 0.4 T 0 and we make this as 0.6 T 0. So, that the sum of these two is equal to T 0, okay. But we change this to 0.4 T 0 and this to 0.6 T 0. If we do that, then the impact of these two currents will be such that there will be a net contribution from this term and this term here, which we will make sure that will nullify the effect from this I b into T 1. Okay. if we can do that, then the midpoint voltage fluctuation over this Ts time period will be equal to 0. Okay. So, this is shown in the next cycle, next table here. Okay. But first I would like to say that, so this means that what we are doing here is T0 by 2 and T0 by 2, instead of having equal T0 by 2, we will make these two multiplicities or these two switching multiplicities to be not equal to T0 by 2, something other than T0 by 2, so that the effect from IB into T1, the net charge, which we can make it, we will try to cancel the effect of IB into T1. But you should remember that this is possible because T0 by 2, tweaking this T0 by 2 is possible because these two vectors are identical vectors. Okay. Remember, we cannot violate the volt second balance. Okay. This is very important, because otherwise, see, we are trying to generate the reference vector OA. Suppose I change this vector or this vector here. Okay. Okay, this vector can be changed. Anyway, if I change this vector, then I am going to change the volt second balance. At all points of time, I have to ensure that the volt second balance must be maintained. Okay. So, that means volt second balance means the weightages of these three, must be properly assigned, so that we come up to this point A. That is the primary objective, and it can never be violated. But here what is the degree of freedom we have? One degree of freedom that we have is we are using this vector 2 times, and now we are saying that okay, we will use these vector 2 times, but of unequal duration, that is the T0 by 2 and not T0 by 2, something other than T0 by 2 for this 2 times here. If we do that, then we will not violate, and sum of this T0. So, if this is 0.4 T0 and this is 0.6 T0, you see I have not violated the total T0 time. So, that means I have not violated the volt second balance. Okay. So, this must be kept in mind. Okay. So, how do we do this is shown in this one. So, here we see that T0 is split into T0 by 2 plus delta and T0 by 2 minus delta to balance the charge. Okay. So, what am I doing? You see here, the earlier that there was T0 by 2 here and T0 by 2 here. Now, I am saying that okay, let us make it T0 by 2 plus delta and make this one T0 by 2 minus delta. Okay. This will ensure that the sum here of the total sum of times is equal to Ts as before. Okay. Only this degree of freedom we have utilized. So, if we change to T0 by 2 plus delta, then the net charge which is flowing out of the midpoint is minus IA times T0 by 2 plus delta, and with this 0 minus minus we have seen that the net midpoint current is plus IA. So, this is the charge which is flowing out of the midpoint. Okay. After we change T0 by 2 to T0 by 2 plus delta and T0 by 2 minus delta. So, now we can equate. So, what we can equate? The net charge flowing out of the midpoint Q is minus IA T0 by 2 plus delta. This is for the plus 0 duration here. For the plus 0 minus duration, we have IB into delta T, this one coming. For this duration, there is no fluctuation. So, we can ignore that one, and then for 0 minus minus, we have IA current flowing for a duration of T0 by 2 minus delta, and this must be made equal to 0, so that the net midpoint voltage fluctuation or the net charge which is flowing out of the midpoint over this time period T s is made equal to 0. Okay. So, that is why we make it equal to 0. So, therefore, if we equate this, we will immediately find out what is the value of delta t needed. So, how much should be the delta t? How much the plus 0 0 and 0 minus minus should be changed? How much delta t or how much time duration away from T 0 by 2 we should include in this switching states is given by this formula. Okay. So, this is one way of ensuring that the net charge is coming out to be 0 over a switching cycle T s. Okay. So, we add some delta t to this plus 0 0 state and we subtract the same time delta t from the 0 minus minus state, and the value of delta t will be equal to so much here. Okay. Yeah, sorry, there is a small mistake here which we should see here. This is I b into T 1. Okay. So, there is a small mistake here, okay, I b into T 1, fine. So, this is one strategy of making sure that the charge is equal to 0. However, although this is an attractive strategy, but we see that with this technique, okay, with this technique the problem is we have to sense the currents. We have to always know what is I b and I a values. Okay. This is not a very big challenge, because in any case for the converter we always sense the output currents I a, I b, I c. For example, it is going to a motor drive, we always sense these currents. Yeah, and if we can ensure that we know that I a plus I b plus I c is equal to 0, then this is not a very big challenge. However, once the another challenge becomes that once suppose for some unforeseen circumstance the midpoint voltage has fluctuated or deviated, how fast it will come back will of course now depend on these instantaneous values of these quantities. Okay. So, this is one. So, we have to depend on the instantaneous ratios of I b and I a in order to see how quickly we can get the voltages back on track. Okay. So, this is one another kind of like limitation of this technique. There is also one more limitation of this technique, and this can be understood from this space vector diagram. So, here you see that, so this is the space overall space vector diagram, and I am drawing the 3 reference vectors means for different modulation index. So, this is like for small modulation index, this is for medium modulation index, and this is for large modulation index, the 3 reference vectors. Okay. So, this is like for the small one. So, this is a small voltage that needs to be produced, and for the medium one like more voltage, and for the higher one the maximum voltage from the converter. Okay. Now, you see the technique of this technique here relies on one important factor, and that factor is we have sufficient amount of T 0 by 2 or to play around with the delta t. Okay. So, if we have sufficient amount of delta t available where we can play around. So, this is basically this delta t and this delta t we can apply if we have a sufficient amount of margin available. That means, T 0 by 2 and this T 0 by 2 should be quite good chunk of the total time period T s. But and this will be happening when the reference vector is close to this vector. Suppose the reference vector is here, okay, then it is very close to this vector here. So, this means that the T 0 time duration for this vector will be very large, and there we have the chance to play around with the delta t. Okay. This will also happen, say for example, if my vector is here, or vector is here, then this vector, okay, if the reference vectors are here, if my reference vector is here or here, then this vector here which is of duration t 0, this vector has a big chunk of the total time T s, and so we can play around with the delta t. Okay, so that the capacitor voltages can be nicely balanced out. However, there is one problem here. If the reference vector is very large, what happens then? Suppose the reference vector is here or here, okay, then you see that the weightage of this vector, this medium vector is maximum, because the medium these reference vectors are very close to the medium vector here, okay, or the middle vector. So, this unfortunately this plus 0 minus we have applied for t 1 time period, and so that delta t, the t 0 time periods are small and the delta t time is also small. Okay. So, that manipulation of delta t will also be small. So, therefore, if the modulation index is very high, then unfortunately this technique has limitation. Okay. This technique the T 0. So, when we are here, when our reference vector is moving on this here, then there is not sufficient magnitude of T 0, and so midpoint voltage balancing will be quite difficult. Okay. So, that is why people have gone for another strategy. Okay. This is for the midpoint voltage balancing using a virtual vector. So, we have seen one technique, we have just seen one technique which has certain limitations, in particular at the high modulation index. Now, we will see a second strategy which has been called the which uses the virtual space vector concept. It came in IEEE Power Electronics letter probably in 2004. This is a very interesting technique which we will see for balancing the neutral point voltage.